This is the third lecture on energy demand. In the previous quiz, or example with Emily, even though Emily's miles driven increased with the Prius, the annual gasoline consumption still decreased. So remember, we were swapping out Emily's less fuel efficient car with a Prius. And so her miles driven increased, but her gasoline consumption still decreased. The gasoline consumption depends on both the characteristics of the car and the decision about how many miles to drive. Given in the equation that we've seen before, QE equals Q times little q times little e, where energy intensity decreases, quantity of driving increases. So both of these factors are changing in opposite directions, and the effect of the improved efficiency dominates. This is the rebound effect. What if the demand for miles driven is more elastic? It's possible a switch to a more efficient car causes the number of miles driven to increase and the quantity of gasoline consumed to increase. If the annual demand for miles driven were given by the following equation, Q equals 16,200 minus 200,000 P, then swapping a Prius out for a Veo would lead to such a large increase in driving that total gasoline consumption would actually increase. I recommend you check this at home. So what is this called? This is backfire. It's an extreme version of the rebound effect. So the definition of backfire is an increase in consumption of an energy commodity, such as electricity or gasoline, due to an increase in the energy efficiency of the associated durable good. Again, this is an extreme version of the rebound effect. That previous definition is essentially a rebound effect, but in this case, the energy service consumption increases by so much that it offsets the efficiency improvements. So you might have a car, you might swap out your car for a car that has higher fuel efficiency, and in doing so, the cost of driving declines so much that you actually drive more than you would have with your previous car, and so much more that you're now consuming more gasoline. Whether we will see backfire from increased energy efficiency depends on the elasticity of demand for the energy service. If demand is inelastic, epsilon is less than 1, then no backfire. If demand is elastic, epsilon greater than 1, then backfire. We usually see a rebound effect, but not a backfire. In econometric studies, usually we find that the demand for energy services is relatively inelastic. As the last slide told us, an inelastic demand curve leads to a rebound effect, but not a backfire. In this case, as durable goods become more efficient, people use them to consume more energy services, i.e. the rebound effect, but total energy consumption will still fall, no backfire. One nice thing about being an economist is that we have a comparative advantage in predicting the rebound effect. Engineering studies often assume people's consumption behavior is fixed, and so engineers might model what will happen if energy efficiency improves, but they tend to ignore demand curves and elasticities. So this leads to an overestimate of the energy savings from an energy efficiency improvement. So if you were a policy person thinking about implementing an energy efficiency policy, and you talk to an engineer and said, please forecast the energy savings that we can expect from a particular energy efficiency policy, the engineer would overestimate the energy savings, while an economist might take into account the elasticity and get a better estimate given the rebound effect. Economists know that the law of demand, but it's easy to know what the price elasticity of demand is. So ex ante, before looking at any data, look at how energy usage responds to energy price changes. So we can just collect some data, and we can relate energy usage to energy price changes. But this is actually hard. It's easy to confuse movements along the demand curve with shifts in the demand curve. So if you've taken an econometrics class, you might have learned about omitted variable bias, and this is a classic problem in estimating demand curves. It's hard to know, which curve we're estimating, a demand or a supply curve, and it's also hard to know whether or not we're estimating shifts or movements in the demand curve. Ex post, we can look at how consumer energy usage changes after they get more energy efficient appliances. So this is what the paper you will read does. The rebound effect isn't bad for consumers. An important note about the rebound effect. Discussions of the rebound effect often imply it's a bad thing because it leads to smaller energy savings than we would hope for with an energy efficiency policy. But this ignores the value consumers get from enjoying additional energy services. In other words, it ignores the welfare effects from energy efficiency policies and more consumption of a particular energy service. Consumers are better off from an additional mile driven or extra lighting. That's what we're getting at here. So next step, I want you to read the introduction mainly to this Cash for Coolers paper, and then we will have an online discussion with the following question. What was the program evaluated in the article, and what was the justification for the program? So as you're reading through the paper, I want you to think about these questions. What did the authors find was the effect of refrigerator replacement on energy use and air conditioning replacement? What reasons did the authors give for their findings? If the rebound effect isn't bad, why might the Mexican government be disappointed? If the same program were implemented in the US, do you think we'd find the same effects? Why or why not?